Okay, last time we talked about the traveling point heat source, and it's a good approximate model for heat flow and welding, and that's the Rosenthal solution. You don't usually have to solve it because most times I want to know something, and we can probably go over this a couple of times again today. You can just use the Fourier number to solve. When I say solve, most times you just want an approximation, and yesterday we went through and showed that if you look at the interaction time for an arc weld moving past a source, or moving past a point, if it's a centimeter long and you're traveling, I don't remember what we said, at 3 centimeters or 0.3 centimeters per second or whatever, and you go through that, you can calculate that the heat effective zone size is going to be about 4 millimeters by just using the Fourier number. Okay, you basically, what we said was when you have, I should probably put this up. Remember we talked about for the Fourier number, okay, for the Fourier number, if I have something that's thick in a given amount of time, the heat will not penetrate all the way through because there's not enough time for the temperature to rise all the way through. When the Fourier number is 1 and the distance and time are such that the temperature on the surface decreases to about 10% of its original value, that's the Fourier number of 1 for a simple one-dimensional solution. Now that's a complex system and you really need to probably go to a fancy model. But when you have a thick solution, if the Fourier number is 10, the heat doesn't penetrate all the way through. It's not saturated with heat. Okay? If something's thin, I have a thin sheet, in the same amount of time, the Fourier number will be small, and essentially the part gets saturated with heat and it's relatively uniform internal temperature. Okay? And most of the time, that's all you really need to know. Now, there are complications, as we said. If the heat flow is convergent, I'm heating it out in the cylinder from the outside, and the heat's kind of concentrating as you get towards the center, then you'll have something that's effective Fourier number that's more like the thin film solution. If it's divergent and I'm heating from the inside of a pipe and it's going out and the heat's diverging, I have to heat a larger mass at a greater radius, and that's more like the thick film solution. But it turns out most times, if I think of all the possible Fourier numbers I might run into, 90 to 95% of the time you find you're either thick or thin. You're either saturated with heat or you're not saturated with heat. It's very rare when you're right on that boundary where it's neither thick nor thin. And so that most of the time you can say, well, did I have enough time to heat this part all the way through? Or what's the distance that the heat travels in the amount of time I have available? Did I saturate it with heat or did I not saturate it with heat? And that's all I really need to know in an engineering sense, and most times I don't care about whether the temperature is 892 degrees or 894 degrees. It's not really relevant. I want to know, did I saturate it with heat or didn't I? Okay, kind of most of the time.
Is the X distance the thickness of the plate?
It's the thickness, or if one example I gave yesterday was heating of a tail shaft. There was the LNG Libra was a ship built over here in Quincy, had a 33-inch diameter tail shaft. And it fractured in the Philippine Sea when the thing was fully loaded with LNG. Just stopped dead, no power because the tail shaft fractured. It turns out it goes back to a defect in the forging from the steel mill. They put it into a cold furnace. Okay, they didn't preheat the steel before they put it into a hot furnace, and because of residual stresses on a part that big. So what's the characteristic heat flow distance? Well, it's being heated. It's a cylinder being heated from, the 12 o'clock position and the 9 o'clock position. So it's only the radius that's important, not the diameter. So in that case, if it's 33 inches, the distance, the characteristic distance for heat flow is 16.5 inches. The radius, not the diameter. But it's also convergent heat flow. And we did a calculation if since it's convergent heat flow, my 16.5, I'll just say let's just say it's 12 inches, and that's 30 centimeters, and we squared, actually I think I have the calculation here. Again. We said, we might as well go through this, since you were here. Time to penetrate 12 inches of steel, 30 centimeters, x squared is alpha t, 900 divided by a tenth, 9,000 seconds. It takes 2.5 hours for the inside to start to warm up if you put a great big piece of steel into that's 33 inches diameter into a furnace. That means the outside is going to go into compression and the inside goes into tension just because of thermal expansion. What you should do in a forge shop is you should put the forging, a large forging like that, into a furnace at a lower temperature for 24 hours and then transfer it to the higher temperature furnace. But they didn't do that. They were in a rush. And they ended up cracking, getting an internal crack due to thermal expansion stresses, a brittle fracture on the inside, because they did improper heat treatment. And it led to failure of a tail shaft and a major problem. For 3 days, they were Lear jetting in parts so an empty LNG carrier could transfer the cargo in an out-of-the-way harbor, you know, in the middle of the jungle in the Philippines. Because if that ship let go, full of LNG, you could blow up something, you know, 10 mile circumference, right? It's a lot of energy.
Do they also put that in an annealing furnace afterwards?
Well, they do heat treatments on it afterwards, okay?
But not per se.
Yeah. It's not on cooling that you really have to worry about this, but it's on heating when things are cold on the inside and you can get a brittle fracture. There's more about that in the failure in the in some of the other part of the course. I actually give a little case study on that LNG Libra and what happened. But anyway, it's not, and we also, this is the one where we estimated the width of the heat affected zone in a steel arc weld, and we said if it's, I guess we had 0.5 centimeters squared per second, and the interaction time, here's the thermal diffusivity of steel, here's the length of the weld pool, the interaction time is the length divided by the travel velocity, and you end up with 4 millimeters. And if you look at an actual weld specimen that's been etched, yeah, it's about 1/8 of an inch or a little larger than 1/8 of an inch. So approximately, that's the number. If I want to know whether it's 4.1 millimeters or 3.9 millimeters, I got to go through all the math. But most of the time, I'm just looking for a ballpark when I'm trying to figure out what's going on. Okay.
So what is the alpha number? Where does that come from?
Alpha is thermal diffusivity.
Right.
Okay. And so I actually gave you a handout of a little thing I wrote in the welding handbook that gives different values of alpha, but just to give you an idea. Somewhere here. So we have copper, alpha is 1, actually gold is the highest, is about 1.2 or 1.3. Aluminum is 0.6, iron is 0.1, 10 times less than copper. Okay, we know we put copper and aluminum on the bottoms of cookware in order to transfer the heat better, right? And that's because steel and stainless steel have very low thermal diffusivities. Okay, and thermal diffusivity just comes out of the Fourier's second law of heat conduction, which is the change in temperature of time. So this is transient heat flow is equal to K over rho C sub P times grad T. Now that you guys know what a grad is, right? So anyway. Yeah, you got to solve that, and the solutions are sort of like these Rosenthal solutions and stuff, and they get a little messy. Not that they're terribly messy, you can solve them on Mathematica just fine. But who wants to go program Mathematica when you can do it in your head? And in fact, for the last 25 years, I've been kind of doing these things in my head. I'll be in some meeting and someone will say something, and you know, they'll be discussing heat flow in solids. Now, this only applies to solids, because once I get to convection, all bets are off. I can't use just the Fourier number because heat's transferred by fluid flow. But in welding, we're often dealing with heat flow in solids. And I'll sit in some meeting and people are talking about this, that, and the other thing, debating on whether the heat is this or that, or the distance the heat travels. And I'll say, well, it only traveled 2 millimeters in that amount of time. And they'll look at me, you know, well, just because I can do the Fourier equation in my head, right? It's not that complex. But, and you know, for estimating, you're in the ballpark. You could be off by a factor of 2, but that's still a pretty good estimate. Okay. But unfortunately, most people in my opinion, have lost the ability to estimate, or maybe that's just not even taught anymore, how to estimate what's going on. And so if you can develop that, it's a useful skill. You can win friends and influence people, measure friends with your ability to come up with numbers. Okay, if there's no questions, I want to start in talking about laser and electron beam welding. Now, I think I mentioned before, these are very high heat intensity processes. These are around 1,000,000 watts per square centimeter. There's no reason generally to go to 7 or 10 million watts per square centimeter, 10 to the 7th watts per square centimeter, because at that point you start blowing metal, vaporized metal away and drilling holes. And I showed you the turbine blades with the holes punched in. And that's actually done by electron beam and laser, although actually today, for a little bit better control on the holes, they're actually getting to plunge EDM. You know what EDM is? EDM stands for electrical discharge machining. And there's two types of machines. One's a wired EDM, where you just have a copper wire going through, and you can cut right through metal by little arcs. A series of, I don't know, it's probably around at 500 or 1,000 hertz, you're arcing, and these little arc sparks cut through the metal. Now, it's an expensive machine, and it's not the fastest process in the world, but it makes a beautiful cut with a very small heat effective zone, because these are very low intensity arcs, okay? Only a few watts per arc, but thousands of arcs just cutting through the thing on a wire EDM. Problem with the wire EDM, in fact, that turbine blade I showed you that had been filleted, so that was cut with a wire EDM, okay? And you can put it back together. There's almost no kerf width to the cut. It's only like 10 thousandths thick on the cut. So that was cut with a wire EDM. Plunge EDM, the reason tooling is so cheap in the world today compared to 20 years ago, the reason they can sell these plastic molded shoes that these kids wear, actually some adults wear too, but you know the ones I'm talking about.
Crocs.
These little sandals?
Crocs.
Well, they're
Crocs.
Crocs. Is because each one of those requires a different size mold. Well, in the old days, each mold would cost you $100,000 because someone's sitting there milling on a milling machine and filing it away and all this other stuff. Nowadays, all they have to do is machine on a numerically controlled machine tool, which someone puts a pattern into the CAD program, and that goes directly to the milling machine, and it cuts a piece of carbon, which is very easy to machine, okay? And you end up with a mold, which you now are going to plunge into a solid piece of steel, and you're going to have little arcs, and it's going to go in there at microns per minute, okay? So it's a slow process, but they call it die sinking, because you're just sinking the carbon as it makes these little arcs. It just eats away the steel. You're flushing the whole thing with some liquid to carry away the swarf, the grinding, you know, the particles that are eroded. But you can make a mold, and now the cost of that mold is $5,000 or $10,000. And so for each size, you can amortize that, and you can have all the different size molds for all those different size feet. Okay. The cost of making molds has dropped by a factor of 10 or 20 because of plunge EDM. Okay, and that's on the last 20 years. And so when you go to Walmart and you see Crocs, you have a different view of why didn't they sell those 30 years ago? They didn't sell them 30 years ago because you couldn't afford to make different sizes, because you had to buy this $100,000 mold for every shoe size. Now you can make them cheap. In any case, I don't remember. They use, for drilling those holes, they use electron beam, laser, and plunge EDM. Very fine little tools that just arc their way through. Okay, and it turns out you can get a more precise hole, more reproducible hole than by melting your way through or vaporizing your way through with laser and electron beam. But aside from that, laser and electron beam are very high heat intensity processes, and we talked before about in a high heat intensity process, you either have to have lots of material to put through there, which is sort of the automotive industry, or you have to have a very high value added part, which is sort of the aircraft industry, where the parts might be worth thousands of dollars per pound, whereas the automotive industry, they're worth $2 a pound on average. Actually, to build an automobile is probably only $10,000 to make it, but once you pay for the health insurance and the marketing and all this other stuff, the automobile you're paying about $5 or $6 or $7 or $10 a pound, depending on the type of car you're buying. But if you actually start dividing the weight of a car into the purchase price, you'll find that you might be paying $5 or $6 a pound, but the actual manufacturing cost is only about a third of that. So it's around $2 a pound to manufacture that car on average of everything that's going into it. So laser and electron beam either have to be used where you have tremendous volumes of product, which is the automotive industry, so you can keep the machine busy. It's a very productive machine. Or you have very high value added, the parts are worth thousands of dollars and you don't care about the cost of welding, you just want the right kind of weld. And in fact, what did I just see? Oh, I just saw something that the US Navy is now using electron beam to weld certain gears together that used to be these are huge gears, as you can imagine on ships. But they used to arc weld them and they'd have distortion problems and other things. Now they're electron beam welding them. It's a faster process, but it also has less distortion. And so you get a high value added there because of low distortion on gears and faster welding. But they switched to electron beam. It's hard to justify electron beam in a shipyard unless you've got a high value added part like a gear as opposed to plating. Okay, plating's not very high value added, okay, in terms of cost per pound. But a gear which doesn't have distortion is very high value added, particularly for sound and other things. Not necessarily for a commercial ship, but for a military ship where sound is important, getting good gears that fit well is a big deal, right? So anyway, a laser and electron beam. Now, it would take me 5 lectures to kind of go through each one of those in sequence. So what I've done is, in about a lecture and a half here, we can go through the differences between these two processes. And so that's what this is for. In 2 slides, I'm going to go through everything you need to know about the difference. Because many people think they're both high energy processes, they're the same. And they're interchangeable. They're not. Okay? In electron beam, am I getting this glare? Okay. In electron beam, you're heating with electrons, and in laser, you're heating with photons. The energy in electron beam is anywhere from 40,000 electron volts to 100,000 electron volts, depending on the voltage of your machine. And I'll talk about that in a second. In laser, you're heating with photons, and the energy of the photon is h times nu, Planck's constant times the frequency. Or if you want, if things are traveling at the speed of light, it's hc over lambda if you know the wavelength of that photon, but it doesn't really matter without going through it. The photons tend to have, in the laser, something like an energy of 1/10 of an electron volt. So the particles, if you will, if we want to think of photons as particles, and electrons, the electrons have something like 500,000 times more energy per particle than the photons in the laser. And there's some important consequences to that, okay? The important consequences of that difference is that in electron beam, the electrons actually penetrate beneath the surface. Typically, if I'm in 100 keV, they might penetrate 1/10 of a millimeter, 4/1000ths of an inch beneath the surface. Whereas on a laser, photons interact with those electrons in the metal, the free electrons in the metal, and it's purely surface heating within the Debye screening length. The Debye screening length, if you remember, is like 10 to the minus 5 millimeters. So again, we've got about 6 orders of magnitude difference in penetrating capability. Now, it may not be very deep penetrating here, but it can be very significant, and I'll show you that. But in laser, it's all heating on the surface. Now, the problem with all the heating on the surface is I'm at the limit where the material can't carry the heat away anymore. If I try to put more heat in, all I do is vaporize more surface. I don't really get heat transfer. Fourier's law is still Fourier's law. The thermal diffusivity of the material is still the thermal diffusivity of the material. I can't force more heat in there, into the solid, by just putting more on the surface. All I do is ablate the surface by vaporization, okay, if I try to hit it harder. And that's how you drill holes. Well, there is a difference here, and I can think of two examples to give you. One time, you know what the camshaft is on an engine?
Yep.
Okay, camshaft has got these little lobes and it pushes the push rods on a piston engine up and down, so the camshaft rotates and these little lobes come around. So it's a long cylinder with these cams on here, and the cams are elliptical shape. And so, well, I haven't drawn that very well. You've got a cylinder with these lobes on there, and every time it comes around, it pushes a rod down and opens the valves on your
That's your timing.
The timing is the timing. Well, it's camshaft's got to be connected to the pistons through the timing belt, right? Anyway, so one time you want to get better wear on those camshaft lobes. So one time, one of the automotive companies, I think it was Ford, decided to do laser surface heating to harden the surface of these camshafts. And when they did it, they built this multi-million-dollar machine to do this, and they got cracking on the surface. Why do they get cracking on the surface? Well, when you heated it up, everything goes into compression on the surface because of thermal expansion. But when it cools down and it quenches and the stuff is hardened, it goes into tension. Okay, so heating is opposite from cooling. If it goes into compression on heating, on cooling it goes into tension, and they got little cracks all over the surface. Very fine little cracks, and you couldn't have that. So what they did, the company Siaki in Chicago built the machine for them, went back to electron beam, and they built a machine in a vacuum that could do this, that would heat treat the surface with a high intensity electron beam. It's not welding, this is just heat treatment. But the electron beam, since it deposits its heat slightly below the surface, the top surface went into tension on heating and compression on cooling. That spot was just beneath the surface. The part that went into compression on heating was just beneath the surface because that's the maximum heating. And they ended up with something that didn't form cracks because the top surface was in compression on cooling, not tension. So the two processes were exactly opposite because one heats on the surface and one heats beneath the surface in terms of a heat treating, surface heat treating type of thing. Now, another example of this is I mentioned a couple of times that back in the early 90s I was asked to go down to the Naval Surface Weapons Center because they had been working on particle beam weapons. And for example, in the Falklands War, where Argentina and Britain were fighting over the Falkland Islands, and the Exocet missiles hit the Sheffield, the British cruiser, and wiped it out, okay? How could a little Exocet missile wipe out a whole great big cruiser? Well, we talked about you can ignite the aluminum and the aluminum superstructure catches fire, and it's the aluminum fire that wiped out the Sheffield. But it was ignited by the Exocet. So the Navy is obviously concerned about people shooting these little missiles at them. It's not that hard to find an Exocet out there in the black market, right? And if a little Exocet can wipe out a whole capital ship, that's not a good thing. It's the old story about, what type of engineer? There's a joke about mechanical engineers build weapons and civil engineers build targets. Okay? Okay. Well, capital ships are sort of targets in today's world. It's just like, I think I told you the story of Tom Clancy's book of the lifetime of a tank in a battlefield.
Yeah.
It's 2 minutes because the helicopters just come in and the tanks are just big targets, right? And you got heat-seeking missiles and so anyway.
Say the same thing if you ask a submariner what type of ships are there.
Yeah.
They'll say submarines and targets.
Right. Yeah, exactly. You know, so in any case, they had, starting in the time of Star Wars in the mid-'80s, the Navy had a big program to develop particle beam weapons. Well, particle beam weapons are nothing more than megavolt electron beams that they wanted to shoot them 30 miles so that you see an incoming missile and you could shoot this particle beam at it. And at the speed of light, you could hit it, and as long as you could direct your beam. The problem was they had something called the hose instability in the beam, and so the beam, in terms of the hose instability, is just like a garden hose that was loose and whipping around with the water coming out of it, just kind of flails around like this. So it turns out the beam They spent $250 million on this, and they learned that the beam had the hose instability, and so instead of 30 miles, they actually could shoot it straight through the air for 30 inches. Okay, so in the early 90s, when peace was breaking out with the former Soviet Union, the Defense Department decided $250 million was enough, 30 inches was not far enough, and they were going to kill this program. And at the time, they brought me in and said, well, we spent all this money, we kept all these physicists busy, what can we do with our technology? And that's when I said, well, you could melt a submarine. You can't weld one, but you could melt the whole thing. At 4 or 10 megavolts per beam, you've got, you know, tremendous amounts of energy. Like you can have, these things are actually pulsed, but you could have a megawatt of energy and you only need about 50 kilowatts to weld. So you got 20 times more heat than you need. But I said what you might be able to do is the Navy has tried a number of times, Navy and other people, United Technologies specifically, the Navy gave them a contract at one time to do what they called laser glazing. And what they wanted to do was lay down weld metal over and over and over again on the surface of a part, a rotating part, and they wanted to build up a very high value added part like a turbine disc, a rotor disc for a turbine. And they built one of these things about this big around. It cost several $1 million because the laser energy, just heating on the surface, you could only lay down a very thin layer. And if you go back to the Fourier equation, the faster you go, the thinner the layer. Only it goes thinner faster than the increase in speed. So speeding up and going faster with a more powerful laser is a losing proposition. Okay, you're getting less pounds of metal down. They were laying down like a pound an hour with this laser process. Very slow process, that's why it costs so much money. And when they're all done, the residual stresses in this part were just horrendous. Okay, and anyway, so I said, well, you might be able to essentially do laser glazing with your electron beams, because now if I actually can penetrate, and if I have a 1,000,000 volt electron beam rather than 100,000 volt electron beam, I can penetrate beneath that surface. I can get around the diffusion equation, because I'm not just depositing heat on the surface, I'm depositing it beneath the surface, and I can lay down layers that are equal to the penetration depth of the heat. Okay? That penetration is not limited by the diffusion equation of heat in the solids. I'm shooting those electrons through there and depositing the heat beneath the surface. So in fact, they gave us a contract, and we did do electron beam buildup. This is actually a manganese, aluminum, bronze, because the Navy's interested in that for propellers, right? This is just a piece of stainless steel, but you can see we laid up beads on here. There are some instabilities, just like the types of going faster and getting humping beads and surface depression on weld pools, and you get defects during arc welding. You can get some of the same types of defects there. This is actually a piece of Inconel that we were basically laying it flat, and you can build up thicker layers with electron beam, okay? And so it turns out you can, and I actually estimated that in certain cases with like I didn't estimate, one of my students did, with 2 million volt electron beams, you could lay down maybe 500 pounds an hour, okay?
So the extra material that you are apporting to the surface, where is it coming from?
The heat? What?
The extra material.
Oh, the extra material, we had a wire feed.
A wire, okay.
So we're just feeding a wire in and melting it as we go along.
Okay.
So, yeah, sorry. You're building it up by, the electron beam is just melting a wire as it comes in. So it's not all that different than TIG welding or something else, but you're using electron beam, but you overcome the surface heating limitation that you have with arcs and with lasers, okay? So you're essentially defeating the heat transfer limitation, okay? And our modeling showed with the 2 million volt electron beam, instead of a pound an hour, you could get 500 pounds an hour. And if you think of 500 pounds an hour, that means I could make a 12-ton casting in a day. However, there are several problems. One is you have to get rid of the residual stresses, which you could do because these relativistic beams could actually do shock stress relief, where you essentially send shock waves through the material and mechanically stress relieve it with shock waves. We did prove that as a principle, but the other problem is 2 million volt electron beams require about 36 inches of concrete as a wall to shield the people from the radiation. It's very high intensity X-rays. So that kind of makes the facility sort of expensive, okay? But potentially, if you're building a ship, they make a bunch of spares, because getting a casting or a forging could take a year or a year and a half as a lead time in building the ship. And so they have to have spares. So they build a class of ships, they plan on some spares that are just going to sit in a warehouse and may be thrown out and scrapped 30 years later, okay? Or they may be used, but you don't know. And the idea was, if you wanted, you could just have a CAD file, and if it took you a week to build up a part rather than a year, you could, no, but you need a $10 million facility. Anyway, so it could be done. But shows the difference between laser and electron beam in terms of heating towards the surface. I think later I'm going to talk about these different types of, yeah, I will. The sample must be conductive. If you're using electron beams, you've got to carry away the current. And if you try to do this on an insulator, the insulator charges up and deflects the beam, and it's no good. The advantage of a laser is you can heat things that are electrical insulators. You can heat ceramics. You can melt ceramics with a laser, because photons don't care. They don't have a charge, and therefore they can heat non-metals or non-conductive metals or non-conductive materials. The electron beam, I say, requires a vacuum, whereas the laser is best in helium. You can use the laser in a vacuum, but it's just an extra expense. Now, it turns out people have actually done electron beam welding out of vacuum. You have to generate the electron beam in a vacuum to get the electrons coming out of that cathode. You have to heat the cathode in a vacuum in order to get the electrons to come out. But people have built machines where you have a high vacuum to generate your beam, and then you have an aerodynamic window that shoots the electron beam through that aerodynamic window, through the air, out into the air. And you actually can see a glow of electrons if you just shoot out into the air. Depending on the voltage, a 75 kilovolt electron beam might create a glow of 6 or 10 inches shooting out into the air. It gets divergent. It's no longer high intensity after about a quarter of an inch, because you've got these electrons interacting with all these gas atoms in the air. But if you're up really close to that aerodynamic window, you actually can get electron beam welds. And it turns out there was a company in Germany and a German scientist who came over to Connecticut and sold in the early 80s Ford on the idea of making catalytic converters. The catalytic converter on your car is 2 pieces of stainless steel. It's kind of a clamshell that comes together, and I have to weld the seam of this thing. And there were General Motors and other people tend to use TIG welding at 4 inches a minute. You got to have like 20 machines to weld the volume of catalytic converters that they've got. But remember, I said electron beam works in the automotive industry because it's high productivity. Ford had 6 machines of these out of vacuum electron beam that were welding the catalytic converters. And the reason they had 6 machines is because they needed 3 of them. The problem was the maintenance on these machines is horrendous, because you got a vacuum system with a leak. Okay? Yeah. I mean, you got it as an aerodynamic window, and you're trying to create the momentum of the gas swirling around this hole to keep the gas going through axially. You're trying to make it go circumferentially by this aerodynamic window, which is nothing, just a circumferential flow of gas. But some of it leaks through axially. And so you were trying to pump the gas out as fast as it's leaking in. And it was just a mess. And Ford used to, the guys at Ford who selected this process used to tout how wonderful this process was. I remember talking to the guys who had to manage the plant, and they just, they were all bald from tearing their hair out. Okay, it was a horrible process for that. So there is out of vacuum electron beam, but in general, if you want to make a high quality weld, because that standoff distance, whether it's a 1/4 of an inch or 3/16 of an inch, is a huge difference in its penetrating capability, okay? Because the beam is diverging so rapidly in the full atmosphere. The lasers actually, you can run them in a vacuum and they run just fine, but it's just the extra cost of the vacuum. Lasers run best in a gas of helium. And the reason for that is helium does have the highest ionization potential of any gas, 24 electron volts. As the laser comes in and heats the surface and vaporizes metal off the surface, you actually can generate, you generate high enough temperatures there, obviously. You got very high temperatures, you're vaporizing metal, that you actually can ionize the air. And if you use argon to shield the weld, argon ionizes at 15 volts rather than 24 volts. If you ionize the air, now you have free electrons above the surface of the weld pool that you're trying to weld, and the free electrons will absorb the laser energy. And I'll show you what happens in a second when you absorb the laser energy, as far as that goes.
What do they use in space? Do they weld?
You mean for space welding?
Yeah.
Well, they do weld in space. Mostly in space, they bolt things together. Things like the space station, International Space Station, they make the parts on the ground, they fit them up, and the astronauts bolt them together. In part because it's not, I mean, when you're in a space chute, weightless, you don't have great dexterity. In fact, what they do is they put them in space suits. They have this huge pool down in Huntsville or Houston or somewhere, and they actually have to do this underwater, okay? When they're somewhat weightless and in this big bulky suit, you don't have much dexterity. The other problem, people have looked at arc welding in space, but you don't have sources of low voltage and high current, and your energy costs in space are horrendous. So people have tried arc welding in space, and you get some very interesting behavior of running vacuum gas tungsten arcs. Vacuum arcs are very different than the high pressure arc that we use here on Earth. And you get some very interesting fluid flow effects. They haven't studied as much as they might because it's arc welding in space for these other economic reasons is not a practical thing. People have talked about electron beam. I wrote a paper about 20 years ago, white paper, wasn't published. Actually, maybe it was published with Professor Masaguchi once later, about 10 years ago, of what you should use in space. Now, you don't want to use an electron beam that's 100 kilovolts because you got the problem of this welder that you got to insulate him from 100 kilovolts plus the X-rays.
Right.
Okay. You could use 40 kilovolts, but you still have the possibility of electrocuting your astronaut. Okay. It would be much easier. You can actually make something that would be like a gas tungsten arc heat source out of a 10 kilovolt electron beam. Now, we would never do that on Earth because it wouldn't be economical to make a tungsten, something equivalent to a gas tungsten arc and pay $1 million for it rather than $10,000 for the equipment. But up in space, where you don't care about the cost of equipment, you could make an electron beam gun. And I have heard, when peace broke out with the Soviet Union in the early 90s, about 6 or 7 years later, I heard that the Soviets had a little hand electron beam gun that they had developed for space fabrication. So when they're trying to market anything and everything to get some cash.
Yeah.
And so back in the mid to late 90s, they were touting this as this little hand electron beam, which I suspect was the same thing that in 1985 I wrote the white paper on about. If you're going to design a welding process for space, what would you do? Electron beam, because you got plenty of high voltage and low current from your solar cells. And that's what electron beam uses. Electron beam is also near 100% efficient, whereas laser is 10% energy efficient, and energy costs you a lot of money up there. If you put together all the different factors, electron beam, low voltage electron beam, which we would never use on Earth, should be the welding process, the fusion welding process of choice up in space. And supposedly the Soviets probably did that, but basically NASA just says bolt it, okay, and put rubber seals in there and stuff, okay. I don't know of any big welding projects in space other than the Soviets used to do studies on it. And they may have built things that I don't know about. And there's possibility they've been welding things classified in space that I don't know about. But in general, the civilian stuff, the things that you do know about in space, it's bolting basically. Okay. Does that answer your question?
Absolutely.
Okay. Turns out the electron beam gives 30% deeper penetration in the horizontal position, and that's because I've got this deep weld pool. If I'm using the capability of having a deep surface depression in my material, some of it's humped up here, every now and then some of that will slump in the vertical direction and fill up the bottom of the hole, and that ends up creating defects, and you saw that in the movie, okay, of electron beam and laser welding. If you do it in the horizontal position, then obviously everything slumps to one side and the thing keeps on shooting because the thing collapses on itself. You still have a hole all the way through if you rotated this 90 degrees. So you get deeper penetration because of that, about 30% in the horizontal position. And so when people are really trying to weld heavy steel, like 6-inch thick steel with electron beam, they do it in the horizontal position because it takes less energy. Okay? You get 50% deeper in vacuum and about 30% in the horizontal position. Okay? Why do you get more in vacuum with the laser? Well, the laser usually, the vaporization is pushing against the atmosphere. If you're just pushing against the vacuum, you get more reactive force to drill a deeper hole. So laser in air or electron beam in air don't drill as deep a hole and don't give you as deep a penetration, okay, in air, as far as that goes. So there's differences there. The electrons penetrate the metal vapor in the cavity. By that I mean, you have a tremendous amount of metal vapor that forms up here because this high intensity beam, in fact, it's the vapor shooting out of here that drills the hole. So you've got metal vapors up here, but the electrons having 40 kilovolts of energy just punch right through that. That's a very rarefied vapor, particularly if you're in a vacuum. But it's essentially a low pressure vapor, and the electrons just penetrate right through as if it wasn't there. However, in a laser process, if you get a vapor up here, this is why you use helium rather than argon, you get a vapor up here, you're going to have problems because you have free electrons up here, and each one of those little 1/10 of electron volt electrons is going, that hits one of those photons, those 1/10 of electron volt photons that hits an electron, a free electron here, will be absorbed by the free electron. And so you won't get the laser beam all the way through. In fact, the shielding gas in laser welding is usually a cross flow. You're trying to blow the vapor away. You're not blowing straight down to protect the weld pool in that way. You're trying to blow the plasma of the vapor away so it doesn't form a plasma. Now, what happens because of that, in electron beam, if you look at a deep penetration electron beam welding when it's all done, you could get something that looks like this. And you might get a little of what we call a nail head up here. But in laser, you'll get big nail heads. You get something that looks like that. And I actually have here, this is actually a laser-assisted arc weld. People have combined it's gas metal arc welding with a wire feed, but they include a laser to add extra heat. And you can see the kind of nail head penetration. You got deep penetration from the laser. Now on that one, part of the nail head is due to the gas metal arc. But just in general, if this is laser, and I have free electrons here, and the photons come in and hit the electrons and then get re-radiated away in every direction, I basically have a diffuse heat source. Part of my heat becomes a diffuse heat source, and part of my heat source becomes a deep penetrating heat source. And in fact, to a first approximation, you can look at the shape of that weld pool and say, that's the shape of my heat distribution on the surface, okay? When I have a heat distribution that's a nice focused line, I'll get an electron beam that looks like this. If I am doing arc welding and I get a very broad, narrow pool, that's sort of the shape of my heat source. if I get a deep penetrating pool like that, I have a more intense heat source. This nail head is a result of a heat source that looks like a nail head. Okay, the molten region looks like a nail head, but the molten head is just mirroring the heat, the intensity of heat on the surface. Okay, and essentially those free electrons create a plasma above the surface that creates the nail head, which is not necessarily bad, but it has to be controlled. Okay, if you get the wrong shaped nail head, you can get some defects in there, solidification. Okay, the electron beam is nearly 100% heat efficient. It's such a high intensity process. I'm not losing a lot of heat to the surroundings. It turns out that it's nearly 100% heat efficient. When people measure it, they measure it at about 98, 99% melting efficiency, by the way. So when I say nearly 100%, it's within 1 or 2% of 100%. Now, a laser is nearly 100% efficient on ceramics. That's supposed to say ceramic. But it's less than 5% efficient on silver, copper, and gold, and aluminum. Well, silver, copper, gold, and aluminum. Anything that has a high electrical conductivity and is a good reflector of light, because let's face it, laser's just light. And if I have something that's a good electrical conductor with free electrons on the surface, it makes a very good mirror. And the problem with laser welding of aluminum and copper, not that we do a lot of gold, but anything that has high electrical conductivity, is you're vaporizing or you're reflecting away most of your energy. It's just a good mirror. And in fact, you use gold-plated copper mirrors for the mirrors to control your laser beams in these high-power lasers. Anybody know why it's gold-coated? Not just straight copper. It's actually, they machine the mirror in its curved surface because you're trying to focus the beam. The beam starts out as a big beam from the laser cavity in a high-power laser, and you want to focus it down to a spot, so you have a curved lens, mirror lens. And it's gold-coated because the copper will tarnish and oxidize. If I have some copper oxide on the surface, the copper oxide actually, being a non-conductor, will absorb laser light, or even a speck of dirt, non-conductive dirt. If I now shine the laser on that mirror, I will burn that piece of dirt and I will pit my mirror. Okay? So you actually have to keep these mirrors scrupulously clean, and you have to keep the copper oxide off, so they gold plate them because gold doesn't oxidize. But it's only because you don't want to have the copper oxide from tarnish build up on the surface of the mirror. That's why you gold plate the mirrors. Okay? So far as that goes. Now, having said that, someday I got to get one of these old two-pane mirrors. There's kind of a the exception proves the rule type of thing here. It turns out that because aluminum is such a good reflector of laser light, people usually think, well, you don't want to use lasers for welding of aluminum. But about 25 years ago, the world's largest application, commercial application for laser welding was welding of aluminum. Okay? And it was for, if you look in a two-pane window, okay, double pane window, it's got a little piece of aluminum sheet that's been made into a box section. And the box section of the aluminum looks something like this. And I want to weld, they just formed this out of sheet metal, and I want to weld that seam, okay? So looking at it 3 dimensions, I want to weld this seam. And these little cutouts, that's where the glass goes. And I got another piece of glass that comes in over here. This is the separator between my 2 panes of glass. And I got some rubber seals and stuff in here. But you don't want this to be a hermetic seal because atmospheric pressure changes back and forth. And so you actually want this to be an intermittent weld. And what happens is they actually they actually do this mechanically now. But in like mid-1980s, I had a number, they make 300 million feet of this stuff a year. And so there was a place in Illinois that had 10 lasers that were all welding this stuff. And they were welding it with a continuous laser beam, but it made an intermittent weld because the process was inherently unstable. You would basically, the power of 10 to the 7th, which is what they focused it to, would come in, couple with only 10% efficiency, which would be 10 to the 6th watts per square centimeter, which is a typical welding situation. So if it only has 10% efficiency for receiving the light, you put in 10 times the power density that you need, but then when you get that, you get some surface depression, and now the laser light is going into a cavity, and in the cavity it's just re-radiating back to itself. And so now, you all of a sudden, once you drill the hole a little bit, you're getting 10 to the 7th, which means you're blowing things apart. And you decouple with all that vapor that shoots out of there. And so you lose your beam, spreads out all over everywhere. And then you recouple, decouple, recouple, decouple. If you look back at these windows, now if you look at windows for the last 10 or 15 years, they're made by mechanical crimping. And you can kind of see the little mechanical crimps along there. But back 25 years ago, they were doing it by laser. So if you look at the right vintage window, and you look in there, you will see these intermittent welds absolutely perfectly uniform. Because they're making it at a tremendous speed, but they were making it with a continuous beam to get an intermittent process. So it's sort of the exception that proves the rule. But if you actually go through and analyze it, it makes sense. You need 10 to the 6th, so you have to put in 10 to the 7th because of the high reflectivity. But then when you depress the surface, you get higher coupling efficiency, which blows everything apart, and you lose your beam. But then once that stuff blows aside, you recouple and start making a weld, and you get this
It's kind of like that
process.
example that you showed us with the beads.
Yeah, yeah. It's not all that different than that, but on a micro, much smaller scale. So one of these days, when they're tearing apart one of those buildings, I got to get one of those samples just passed around or something, because someday there'll be a collector's item, right? For everybody teaching this course, which is me. Okay. So actually, let's cut through this pretty quick. One of the things, I guess I haven't said it, let me go back to this thing before where I said that the voltage of the electron beam is 40 to 100 kilovolts. Now, why is that? Turns out electron beam machines usually go up to about 40 kilovolts, but you very rarely, I'm not saying you don't, I've seen 60 kilovolt machines, but usually there's a big gap, and you go from 40 up to 100 or 150 or even 200 on commercial machines. And the reason you don't have things in the middle here, you do have a few machines, is at 40 kilovolts, just the vacuum chamber will shield you from the X-rays. These are not very hard X-rays at 40 keV. Okay? At 100 keV, you got to have lead shielding on your vacuum chamber everywhere, or you got to clear everybody out of the place where the beam is. So if you're going to go to the expense of, or you're going to go to higher voltages, which has certain advantages in terms of deeper penetration and things like that, better focus, and we'll talk about that later. Lower currents is the real reason. Okay, with lower currents, you can get a better focus to your beam, which we'll talk about that tomorrow. But if you want to go to higher powers and higher currents, you usually don't want to go above about a half an amp. So you're limited to 50 kilowatts if you're using a half an amp at 100 keV, but at 40 keV you'd be limited to 20 kilowatts, and 20 kilowatts is probably going to limit you to maybe half an inch thick material. If you really want to do thick section electron beam, you got to go to these higher voltages, but then you got to have the extra cost of X-ray shielding. Okay, there's not very many machines that operate in between, because then you have to have X-ray shielding, the extra cost of X-ray shielding, and you don't get the advantage of deeper penetration. Okay, so I'll probably leave that there, and that's enough for today.